All right, we're back. We are on page 7 of notes 4 of Calc C. We're talking about infinite series. We just did a lot of stuff with geometric series. You really want to become an expert on those because they come up all the time in a lot of different contexts. And they're kind of like one of the basic series that you'll find yourself using just all the time. So let's look at this next series. You'll notice right away this is not geometric, right? So we don't have some quantity being raised to the nth power, which is essentially what you get with a geometric. So this says, investigate the sum from 1 to infinity of 1 over n minus 1 over n plus 1 by writing out the first 7 terms and the general term of the series, and then simplifying. What do you notice? What do you suppose the series sums to? All right, so let's see if we can deal with this. So I'm going to write out the terms. What I think is useful is to like put them in parentheses so that you can really clearly identify like what n value gave you the thing you're looking at. So when I plug in 1, I'm going to get 1 over 1 minus 1 over 2. And then plus, you get 1 over 2 minus 1 over 3. Already you can maybe figure out what's going on, or at least see what might potentially happen. 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5. So as with all things, I feel like this is an excessive number of terms when you don't really need it to work out the pattern, but whatever. Plus 1/5 minus 1/6, 1/6 minus 1/7, and here we go, plus 1/7 minus 1/8. All right, so is that enough to like figure out what's going on? I mean, I think it's definitely enough to figure out what would happen if we went to infinity. So here's what's happening. We have 1 over 1, and then it's minus 1/2, but then the next thing gives us plus 1/2. So those are just going to cancel. And then the next one, we get minus 1/3, but then we'll get plus 1/3. So those are going to cancel. And then minus 1/4 plus 1/4. And if you look, you can see that this is going to continue all the, like literally all the way through. I mean, it's not going to stop until we get to this one last thing. So there's like a last thing left over. So if you go, all right, I tried to use a different color all the way through. I think I did. The only thing we're going to be left with here, if we were to simplify this, so if we found this partial sum, it's 1 over 1 minus 1 over 8. Everything else is gone, right? So what if we went from n equals 1 to k, right? So the kth partial sum. So if I were to say s sub k, I mean, this is literally going to happen, right? So I'm going to still have 1 over 1. All the intermediate pairings are going to collapse on each other, right? So plus 1/2 minus 1/2, plus 1/3 minus 1/3, all gone. The only thing I'm going to be left with, if I'm going up to k, is going to be minus 1 over k plus 1, which means that if I want to figure out what the series sums up to, I can actually do it in this case because I just need to take the limit of the kth partial sum. So if I do the limit as k approaches infinity of s sub k, it's going to be the limit as k approaches infinity of 1 minus 1 over k plus 1, which is definitely 1. So this series we were actually able to find the sum of. This series is called a telescoping series. Stop it. That was Siri trying to get involved again. This is called a telescoping series. And the reason, think of a pirate's telescope, right? Where like you want to see something, you like pull it way out and then you look, right? So that's what we mean by telescoping. It can collapse on itself and you just end up with like that first lens and that last lens, I guess, like when you collapse. I don't really know how those telescopes worked at all. But you know, the last part and the first part are the only part that you see when you like just collapse it down on itself when you telescope it. So telescoping series are going to be series that we can actually find the sum of, which is fairly unusual. Like geometric, we did it, we could find the sum. I probably didn't mention this because I wasn't really thinking about it. It's unusual to be able to find the sum. It's very common to know that it has a sum, but to be able to find like a finite value or a clear, like this is the value type situation, weird. It's not as common as you might think. Certainly not based on what we've currently done. All right, investigate the series from 3 to infinity, 1 over n plus 2 minus 1 over n minus 2 in a similar fashion. So it doesn't tell us how many we need. We're gonna go until we think we see the pattern, I guess. So let's see. So I'm gonna start off with n equals 3, and that'll give me 1/5 minus 1/1, I guess. And then plus n equals 4, 1/6 minus 1/2. N equals 5, 1/3. I'm not seeing anything yet. So this was 3, 4, 5. So we'll go with 6. So 1/8 minus 1/4. Nothing. Okay. 7. 1/9 minus 1/7. Okay, here we go. So something has happened. So we've got our first cancellation here. Plus 1/7 minus 1/7. All right. Let's see where we're going with this. So what did I plug in there? That was 7. That can't be right. 7. What did I put? 6, 7. Oh no, we didn't get our first cancellation. That's disappointing because this is not that. This is 1/5. What did they always differ by 4, right? So let's speed this up. Plus 1/10 minus 1/6 plus 1/11 minus 1/7. All right, something had to simplify here. Oh, I didn't even notice. We had one earlier. Oh my God. We had one earlier, which I didn't notice. It's minus 1/5 and plus 1/5. Those canceled. Now 1/6 plus 1/6 minus 1/6. Oh, geez. And then, okay. So I think I see maybe what's happening. Minus 1/7. Now, the real question is, I'm going to use, let's see. What color should I use? I'm going to use this bright pink color for the things that I think are never going to cancel out because we will never loop back to them, right? It took a while, but eventually we were able to cancel out here. This is where the cancellation starts. 1/5 will go, 1/6 will go, 1/7 will go. The issue is we're never going to get back down to minus 1/1, minus 1/2, minus 1/3, minus 1/4, right? The next term that I add is going to knock out the 1/8. Then the next one will knock out the 1/9 and the 1/10 and 1/11. And that's going to continue forever. The thing that's never going to go away are these bright, well, they're bright pink on my iPad. I don't know what color they are on the recording. It does not look like the same color, but that could be like an angle thing because I'm not like dead on with this. So let me say here, these are going to stay. Everything else is going to go, right? So I would say that the sum of this is going to be negative 1/1 minus 1/2 minus 1/3 minus 1/4, which is what? I don't know. Should we use 12? So it's going to be negative 12 plus 6 plus 4 plus 3 over 12, which is 10, 13, negative 25 over 12. I think that the sum is going to be negative 25 over 12. I don't really want to write out like what the partial sums are because it's not really clear to me exactly from this what I would have to write out. And also I'm pretty confident that I've got the sum. So this is another telescoping series. So a telescoping series is a type of series we can find the sum of, provided a finite number of terms don't cancel out, right? So everything except a finite number of terms will cancel out. So this is actually our next series test. So series test number 2 is for telescoping series. And basically, a telescoping series is just one in which nearly all the terms cancel, leaving a finite sum. That's a convergent telescoping series. I guess it has to, because implied in the name is that it's basically going to have a finite sum because it's got a telescope, right? You got to cancel things. So that's how you can evaluate them. You can go through this process where it's a little complicated. I will say, so I've never done the math on this, and I think somebody did it in one of my classes one year and kind of came up with something they thought was reasonable. you can sort of tell when it is telescoping, you can kind of tell how many terms are going to be left based on how far apart these are, right? So what do I mean by that? Like one of them is n plus 2, one is n minus 2, so they're like 4 apart, right? Like say you're at n, you can go to n plus 2, n minus 2, they're 4 apart. So it's going to leave 4 terms, which is like a really interesting observation. So here you have n and n plus 1. They're 1 apart, so it's ultimately just going to leave 1 term in like the final evaluation, which is kind of interesting. If you're interested in that, definitely look into it, see what you can come up with. Let's see if we can do these. So find the sum of each of the following series. So here, for example, I'm expecting there to be 3 terms left over because n and n plus 3 differ by 3. So let's see if that's what happens when we do this. So first, n equals 1 gives us 1 over 1 minus 1 over 4. N equals 2 gives us 1/2 minus, not plus, minus 1. So they're always 3 apart. So 1/5 plus 1/3 minus 1/6 plus 1/4 minus 1/7. Okay, so they're always, okay, so it already started canceling. So I'll do one more term just to like 1/5 minus 1/8 plus dot dot dot, right? So how did this work? So minus 1/4 canceled with 1/4. Minus 1/5 will cancel with 1/5. Minus 1/6 will cancel with the 1/6 that we're ultimately going to write here. So now everything will have canceled except for 1 term, 2 terms, 3 terms. And then that's all that's left over. So this is going to give us a sum of 1 over 1 plus 1 over 2 plus 1 over 3, I guess. So what are we doing here? So that'd be 6 plus 3 plus 2 over 6, which would be 11 over 6, I think. Yeah, 1 plus 5, 6, 11/6. Okay, so I mean, it works. And let's take a look at this one last example where we have to do some work. So this is a really common thing to do with these problems. You often need to do partial fraction decompositions, which, who saw that coming? Maybe if you like thought, if you were in that frame of mind, you might have thought, I bet partial fractions involved somehow. So we have to decompose this, but we can just use the cover-up method, which is definitely what I'm going to do. Every time you can use cover-up, you should, because it's the fastest. So if we let n equal 0, we'll know that a is equal to 2 over 2. If n is equal to -2, we'll know that b is 2 over -2, which is -1. So really, we're doing the sum from 1 to infinity of 2, nope, what am I even doing? 1 over n minus 1 over n plus 2. So they're 2 apart. So I'm expecting there to be 2 terms left over at the end, which is just like convenient to know going into it. If we had gotten 1 over n plus 1 over n plus 2, it's just going to diverge. Like you're just adding stuff over time. Actually, that's not really obvious, but it would diverge, but we don't necessarily know it yet. So here, if we plug in 1, we get 1 over 1 minus 1 over 3, 1 over 2 minus 1. They're always 2 apart, 1/4. Plus the denominators, I guess, is what I'm referring to. So, all right, so canceling. We've already got our first cancellation, minus 1/3 plus 1/3. I'll do like a couple more just to show what's happening here. 1/5 minus 1/7 plus dot dot dot. But definitely, I mean, I would say definitely what we thought was going to happen has happened. Minus, but then this knocks it out, and then minus 1/5, and then this will knock it out, and then it's just going to keep going forever. So what are you finally left with? This will never cancel. This will never cancel. So this whole thing is going to be equal to what is happening there. Sometimes it turns my lines into into nice horizontal segments, which is great, except it slows it down and also does this weird thing like on the iPad screen that I can't really deal with. So I get 3/2 there. So don't forget, if you need to do partial fractions, your calculator can do it. For some reason, it's the expand command, and I'm sure there are videos of that, and you've definitely, if you've done partial fractions, you've played around with expand. All right, so that's basically telescoping series. There's not a lot to them. They've not been on the AP exam, maybe ever, I'm not really sure, but certainly not in a while. And so I'm gonna end this here, and I'll come back in the next video and do more. So I will see you there.